starting to record. Okay, I hope that you can see what I'm showing pretty clear. Well, this is a very simple case, let's say. This is just a continuous beam. Okay, it's gonna be like this for 1 hour. Apologies. It is a continuous beam over 5 vertical supports, basically, okay? So it is something that you have qualitatively already seen, but this time I am just considering different load conditions, different lengths, and 3 redundancy degrees. So that's a pretty, yeah, I am already recording. I think recording, right? Yeah. Okay. Happening? No. Obviously not. Okay. Let's do like this. I don't know what. Okay. So this is the example. I am keeping the laptop on because we will see how we can use Excel and TeleIoT to solve this example, to check our results. And I don't know if you are acquainted with Excel. Do you commonly use it? Yes, no? Sometimes, okay. So now you know how to compute, to make a computation with Excel, okay? Even with matrices, like a matrix. Okay, you can see this will be new for, I think, I hope all of you. And I think that can be helpful for the future because it's just something very easy and related to linear system. So it applies basically to everything. So this is the example. I just spoiled that we have 3 redundancy unknown. So as usual, let's just free the rotations. In correspondence of the internal supports, and every time we release something, we release a motion, so we release the restraint, we have to add the corresponding static unknown. So in this case, we have x1, x2, and x3. Okay? So Q1, Q2, Q3, no, Q2, and Q1. The values of Q1 and Q2 are here. But people at home can see IOPS. Yeah, because you can pin the window. I don't know why it keeps losing it. So, well, this is not everything. We have still to add our conditions, our compatibility equations. So the rotation in node C has to be equal to 0. Rotation in node E equal to 0. Actually, the relative rotation between this beam and this beam, and the relative rotation between this beam and this beam in the node E, and in the node C, and in the node G are equal to 0. I'm going pretty fast because, I mean, you have seen all of these. The interesting part is later. So we want to fix these three equations. We have that the rotation in C, E, and G depends on x1, x2, x3, q1, and q2. So we apply the superposition principle. So we, first of all, we consider only the external loads. So we have Q1, Q2, Q3, Q2, Q1. Please consider that this can be, for example, a lively footbridge. In Italian, it's una passerella pedonale. And we always have to consider different load conditions when we do some computation, when we design the structure. It holds also for residential buildings, okay? This can be a continuous beam over several columns. We have to consider that some spans can be alternatively more loaded than others. And we will see it in the, I think, next week, because I don't think I have time to end all the stuff. Okay? When we consider the structure undergoing these loads, we have to think which is the influence over these three rotations. So we draw the deformed shapes. We know we are interested in this, and only these angles. We don't care about this, we don't care about this. So, the relative rotation in the node C associated to the load, we can consider the load case 0, because we are not considering the static unknowns, is this one plus this one. Okay? This one is, we have seen this a lot of time, it is the load as, that is exciting this beam, so Q1, times the length of this beam, which was L1, to the power of 3, over 24 times, this is something I forgot, I gave you all the information about load condition and the geometry, but I didn't say that this is iota. It has a specific value of Young's modulus and a specific inertia moment. These and these are the same, just to make easier computation. Otherwise, that would have been way too long. Okay, this is the rotation in the first beam, AC, and plus the rotation in the second beam, CE, yes, which is qualitatively the same, but the load this time is Q2 times L2 to the power of 3, 24 iota. Same stuff for the relative rotation in the node E, associated to the same load condition. We have this, that is Q2 times L2 to the power of 3 over 24 iota, I'm doing this for the people at home. I don't know. I think it helps, but I don't know. Plus, plus the same stuff, because here we have same load and same span. Okay, so it is twice this stuff. It means we can simplify 2 and 24. It is 1/12. Then we have the rotation in the node G. G. This is equal to basically PC0, because we have this first rotation, which is equal to this one, and the second rotation, which is equal to the first one, because it's all symmetric. So it is Q1 L1 to the power of 3 over 24 iota plus Q2 L2 to the power of 3 over 24 iota. Okay, now then consider the influence of only x1. Okay, so we have the generic x1 applied. We don't know its value, but we know that if we apply a counterclockwise moment in the node C in the beam AC, we will have here a counterclockwise rotation. Same stuff, but with opposite sign in the other beam, in the adjacent beam. Then we will also have a rotation in the node C, but we have no rotation in the neighboring beams, because here we have possibility to rotate. So that's easier, because we only have phi delta phi in C for the load x1 equal to x1 times L1, that is this rotation, over 3 iota. Is it anything new for you? No? I mean, you have already seen this stuff, right? Okay. I'm sorry, this will be boring for still 5 minutes, then it will be worse. I don't know. The rotation in the second beam is the same qualitatively, but the length is different. Okay? The rotation in the node C, no, the second was E, will be x1 times L over 6 iota. And the L is the length of this beam, so L2. Now, it's like this on purpose, for some reason. Okay, can I go on? Have you already copied it? Okay. So we can consider the case where we release only x2. So in this case, we have rotation both on the node where x2 is applied, and both in node C and in node G. Delta phi C2 is equal to x2, because it is the rotation in a simply supported beam in the opposite node where a bending moment is applied. So this is its value. And we have E, delta phi E2 is x2 times L2 over 3 iota, okay? Because it is the rotation in the node where the bending moment is applied in a length, in a beam whose length is L2. And here we have the same geometry. So we have twice the same contribution. So 2 times x2 times L2 over 3 iota. And that's it. Because we have this one plus this one, which are the same. No question? Then the rotation in the node G when x2 is applied is basically, if you think about it, is exactly the same, the first one. Okay? Because we have only this rotation, which is the rotation in the node opposite to where the bending moment is applied in a beam whose length is L2. The bending moment is still x2. So we have this stuff. Again, we have a good symmetry between node G and node C. Okay, now the other, I will make it here. Okay, now this time is the third case. We release only x3. We draw the deformed case. And we have only influence on this very node and the adjacent one. So again, delta phi E associated in the third case is equal to x3, because this time the bending moment is x3 times L2 over 6 iota. And the rotation, the relative rotation between this beam and this beam when x3 is applied in that node is this rotation, which is x3 times L2 over 3 iota plus x3 times L1 over 3 iota. Okay, do you agree? Whereas, obviously, the relative rotation in this node is 0. And I didn't find it, but the relative rotation in this node is 0. And that's all. Okay. So we have all these terms. We can combine them into an equation. 3 equations. Okay, I will clean up this one. Maybe I will just to save some room. Okay, So we had our three compatibility equations. Okay. I will follow this just to. Equation number 1. What did it say? That the relative rotation in the phi is equal to 0. So we had delta phi 0 plus delta phi C1 plus delta phi C2 plus delta phi in the node C in the third scenario. The sum of all these four terms has to be equal to 0. Now, if we just copy-paste all the terms, we have this is Q1. No, we move this in the last term, and you will see why. So first of all, we consider the first one, so when we release x1, and we have x1 multiplying L1 plus L2 over 3e iota. This was this one. Okay? Then we have the second one. All this stuff are plus because all the rotations are coherent. Okay? So we don't have to care about the sign. x2 multiplying L2 over 6 e iota. x3 is 0. And then we have this term plus Q1 L1 power of 3 plus Q2 L2 to the power of 3 over 24 iota. These three terms have to be equal to 0. Similarly, if I'm going too fast, please tell me. Okay? That's just I mean, that's all trivial. That's just long and boring. But we have these four terms in the node E, no more C. I don't copy-paste this because it's lame. I only substitute these values, and we find x1 multiplying L2 over, this is L, 6 iota. Then we have, and this is the influence of x1 over this rotation, plus x2 multiplying twice L2 over 3 iota. Then we have x3 L2 over x iota. And then the term associated to the external load, which was, I made a mistake. Okay? Please be careful every time you do this test, because it's okay, it's lame, it's you can say boring, but you have to be very careful about what you are adding. And I knew that I made a mistake, and now I found it. So Q2 L2 L to the power of 3 over 12 iota. But don't worry, the results are right. Okay, this was the second equation. The third equation was delta phi the rotation in the node G. It will be 0. We have that when we release x1, we have no influence over the rotation in this node. But when we have x2 and x3, we have the terms. So x2 multiplying L to the x, yeah, L2 over x iota plus x3 multiplying yep, L2 over 3 iota plus L1. Okay, and then we have the known term, I mean, the one that is not associated to any unknown, but with the external load, which is equal to Q1 L1 to the power of 3 plus Q2 L2 to the power of 3 over 24 iota, equal to 0. Okay, do you agree? So far, I mean, nothing new. It's just worse than what we did before, because we don't have 2 equations, but we have 3 equations. Now, before I move on, consider that is there anything that we can, is there any information about this structure that we can exploit to make our computation easier? You know that. Perfect, okay, the symmetry. So if the structure is symmetric, from a geometrical viewpoint and for the load, what do you expect about x1, x2, and x3? Or not all of them, but few of them. Come on, I know that you know. Perfect. Yeah, because there is no reason why they should be different. So x1 has to be equal to x3. So far we have 3 equations in 3 unknowns. So we should say, okay, I have x1, I put all this stuff on the other side, and I know x1 as a function of x2. Same stuff here, I explicit x3 as a function of x2, and I substitute x1 and x3 in the second unknown, in the second equation, so that it is only function of x2. So I have one equation in one unknown, I find x2, and then I substitute here, I find x1, I substitute x2 here, and I find x3. So that's a lot of passages. But if we exploit the symmetry, that's easier. Okay? Because we can just get rid of one equation. We have 3 equations with 2 unknowns. So, if we do all the computation, we can end up with, this can be our equation 4, okay, because it is a new information we add that is due to our comprehension, to our understanding of the structure. If we don't consider this, we can obviously solve the structure. It will just take more time. I don't want to go into the details because many of you would faint. But from the equation 1, we can we can use just equation 1 and equation 2 plus the information coming from equation 4. So we can end up saying that x1 over 3 plus 2 over 3 x2 minus 2 L2 to the power of 2, 12. And this is from this, from the equation 2. If we substitute this information in the previous equation, we find that x1 will be equal to minus 2 x1 L1 to the power of 3 plus 2 L2 to the power of 3 over 16 times L1 plus 12 times L2. Then we take this stuff. We know Q1, we know L1, we know everything. So we find the value in x1, which is a bending moment, so it will be kilonewton times meters. We substitute this value here, and we find x2. Now, let's just see it with equation. Ah, no, okay. Just something more so that we can appreciate it all at once. Okay, this is the resolution of the problem. And if we use Excel, that's trivial. We just say that in Excel it is equal to minus la la la. Okay, and but we are going to see it in a while. The more advanced way is exploit the. Ah, now it goes all the way. Oh, okay. I fooled myself. Sorry, guys. Can I clean this up? Okay. Because you have seen with Professor Gentile just once, so maybe you didn't pay so much attention about it, about the matricial form of this linear equation. We can consider as we have three unknowns, x1, x2, and x3, multiplied times 0 in this case. x1, x2, and x3. x1 is 0, x2, and x3. We have three linear equations in the three unknowns. So we can see as if it was a matrix of coefficients times x1, x2, and x3 equal to minus, equal to something, equal to a vector. When I draw square brackets, this means that it is a matrix, so I have more than one dimension both in the rows and in the columns. When I draw these brackets, I only have a vector. Okay? So many terms in a column or in a row, depending. So we have the row of equation 1, the row of equation 2, the row of equation 3. In equation 1, I want to just write all the coefficients that multiply times x1, then x2, and then x3, equal to the known term, the known vector, that I have brought on the other to the other side of the equation. So x1 is multiplied times this stuff. Before I go on, something that we can do to ease our computation is just multiply everything times e iota, because they are the same. Okay, so if we multiply both this term and this term times e iota, they just disappear. So that's easier. In the first equation says x1 is multiplied times this stuff. So we put this L1 plus L2 over 3. Okay, then the second unknown is multiplied times L2 to the power of 6. x3 is multiplied times 0, because it does not appear. So this matrix, this first row, just says, this is the coefficient of this unknown. This is the coefficient of this unknown. This is the coefficient of this unknown. Then there is something that is not multiplied times this unknown. And it is the effect of the external load. I have to make it bigger, maybe. And it is equal to minus Q1 L1 to the power of 3 plus L2 Q2 L2 to the power of 3, so 24. And the minus multiplies everything because I'm saying that I have brought this on the other side. Okay, is it clear how this is built? Okay, we can do the second one. So we write this equation in this form, and this time you will help me, and you will just tell me how much is the first coefficient, how much are the coefficients of this matrix and the known term. So in the first column, what do I have to write? So in the equation 2, I'm looking at it, I'm saying, what is multiplied times the first unknown? Okay, good. Perfect. The second one? Come on, don't be shy. Yep. And the last one? Okay. On this side, not you? No, not you, someone else. Oh, here? Over? Okay, perfect. That's nothing against you, it's just to other people. Okay. The last one, I will do it because it is easier. X1 does not appear. Okay, so we have 0. Then we have L2 over 6. Then we have L2, L1 plus L2 over, no, over 3. And there, minus Q1, L1 to the power of 3, Q2, L2 to the power of 3, 24. Now, two things about this stuff. This matrix has to be symmetric every time. It does not depend on the fact that our structure is symmetric. Okay? It is not related to that. The fact that because this is, what does it mean that it is symmetric? It means that if we get rid of the elements on the diagonal, the entries that are in the second row, in the first row, second column, are equal to the second column, first row, second column, second row, first column, first row, third column, first column, third row. All these terms are equal, okay, are symmetric. And the terms in the diagonal have to be positive. Okay? If there is something wrong, if these two conditions are not fulfilled, I know that I made some mistake. So I should go back on the equation and check it before I end up with the wrong result. These terms, I don't care. Okay, now let's see how we can solve this equation. I have to share it. Okay. Well, okay, first of all, I hope that all of you are acquainted with Excel, but I know for sure that many of you are not. So let's start with the basis. First of all, we have to add our entries, okay? So our entries are Q1, Q2, L1, and L2. Everything depends on them. Q1, Q2, L1, L2. Q1 is equal to 5 kilonewton over meter. Yep. Oh, yeah. Sure. Okay, better. Okay, so please keep in mind, I'm just drawing this to remind me what I will put in the adjacent column. In this column, have to be present only a number. I also can say equal to 5. It's the same. Q2 was equal to 20. And the units are kilonewton over meter. This is just something that I draw to remind it. Whereas L1 was 10 and L2 15. Right? Yeah. So far, very trivial, I have just added terms. Okay? Now I have two possibilities. Or I solve the entire problem by hand, and I end up with something that I cleaned up, and that was equal to x1. So I know the algebraic resolution of something, so it is just a formula that I have to solve. And it was x1, if you recall the stuff that we did before, it was minus, so equal. When we add a formula, we have to insert the equal sign, minus, then we have a ratio. So we have to open the brackets. 2 times Q1, so we insert 2 times the multiplication sign, and then we select the cell where we have added the value of Q1 times L1 to the power of 3. This is how that is computed. Plus Q2 times L2 to the power of 3. We close the brackets, and we have written our denominator. Then the division sign, and we add the denominator. It was 16 times L1, so 16 times, we just click on the cell where C5, where we add the value of L1, plus 12 times L2. We close the brackets, equal to minus 227.94. Okay. If we vary anything, so we just have to change the load in the data. Since it is just a formula, the result will be updated immediately. But let's see how to write this. That is much better. So that you can do it when you, for example, compute your homework. That's very easy, I mean, to write that stuff, right? So in this case, you will need no more one cell where to write one equation, but more cells. Because we have to write this 3 times 3, so we need 9 cells for the matrix, and this 3 times 1 vector. So just to make it easier to understand, we draw the plot, we draw the lines. This is the matrix of the coefficient. In the first term, there was L1 plus L2 over 3. So we have ratio, again, equal, because we are inserting a formula, and we expect for a result, a numerical result. We open the brackets, because we have a ratio. L1, we just click on that cell, plus L2. We close the brackets, over 3. It is 8.333. The second term, first row, second column, L2 over 6. So we just equal to, we select this, over 6, 2.5. The third one is 0. Then again, this is 0, this is as before. No, over 6. Again, I'm just filling up all the diagonal terms, all the non-diagonal terms. Then, in the diagonal, the second term was twice L2 over 3. L2 over 3 equal to 10. And this is, yeah, I am sharing it. L1, again with this stuff, plus L2 over 3, yep. Okay, so far we have this matrix. Then we need also the known terms vector, which is this one, which is equal to, okay, the first term is minus a ratio, so minus, we open the brackets, Q1 times L1 to the power of 3. Q1 times the multiplication sign, L1, this sign to indicate the exponent, 3, plus Q2 times L2 to the power of 3. So we know this was the denominator over 24. This is a huge number. Let's check if it is. Okay. The second term was minus Q2L2 over 3 plus over 12. Just something. Obviously, I have inserted the brackets before, not because there is a ratio, but because we have a numerator where we have more than one term and then the denominator. If I didn't put the brackets in Excel, I would have written just minus Q1L1 to the power of 3 plus this stuff over 24. This is different. That would, this is what I would have written if I didn't put the brackets. The brackets tell me that all the stuff inside the brackets is divided times 24. Minus Q2 times L2 to the power of 3 over 12, yes. And the second, and the last case was the same as before. Okay, that was symmetric. Now, how to compute the vector of unknowns? We know that our vector of unknowns has to be 3 times 1. Okay? Okay, don't worry, it's almost done. I know that you have 2 hours of break. I'm not wasting 1 hour. I'm just ending this exercise. So we select 3 times 1 column, 3 times 1 cells. The equation is, it may vary for English or non-Italian version, but the logic is the same. We have, as if it was a matrix A times X, which is a vector. A with 2 lines means we have 2 dimensions because it is a matrix. X with 1 line because we have only 1 direction. Equal to B. From linear, if it was an algebraic system, and it is, the solution is very simple. We just multiply this term and this term times the inverse of this stuff. Okay? So this is the solution. So we have to multiply the inverse of this matrix times this matrix. So it is, the equation is matre.prodotto, but if you use a non-Italian version, the name of the function may vary, obviously. we open the brackets, the argument of this function will be the inverse of this and this. So, matr.inversa, and we select the entire matrix. We close the brackets. Here, Excel suggests us how to write our stuff. So, matr prodotto between two matrices requires that you write the first matrix and then dot comma the second matrix. So, we have written the first one, dot comma. The second one is just this one. We select not one cell, but the vector. We close the last bracket. Then to get the result, we have to press Ctrl, Shift, Enter. Okay? So that in this column, we get the result. So minus 227 is the same as what we computed before. Okay? Now let's do it very quick with Try2D. But I have to stop this sharing and share everything. Whenever you want. Okay. So we have this Try2D window. We create a new one. We create, first of all, the nodes. The first one in the coordinates 0, 0. Okay. Then the first length was 10 meters, so 10, 0. Then we add 15, so we have 25, 0. Then we add again 15, which is 40. And then we add 10, and we end up with the last node in coordinates 50, 10, 50, 0. Then we create the element. We connect all the adjacent nodes. Then we need the restraints, so attribute node restrain. Node 1, we restrain both the horizontal and the vertical displacement. And then we select all the other ones, and we end up with vertical supports. Now the loads, so attribute beam, because it is a distributed load. The first and the fourth beam undergo minus 5 kilonewton times meters. Whereas the first two ones, the other two beams, undergo minus 20. So here we have set everything. We need only to decide a material, for example, steel, a geometry, what's happening, I don't know. We select just a random cross-section. Why we select just random cross-section, in your opinion? Yeah. Because the structure is homogeneous, so nothing depends on the on the section and on the material. The only thing that matters is the only thing that is influenced are the displacement. But now we are not still looking at them. So just to solve the structure, we can add whatever. We solve the structure, we find the diagrams of bending moment. We see that the bending moment in the node 2 that is associated to our C is minus 227.9. And with Excel, we had found this, 227.94. minus 448 times 5, this one. Okay. So basically, this is what I wanted to show you, how to use Excel to solve algebraic system, and how to check the results using both Excel and TLIA2D. This can be helpful for you no matter what you do. Now, I know that you have just one, I know that I have already exceeded the time of your lecture, but I would like to go on. So if you need to get out and have a break for lunch, you are free. I am going on and I will record everything. So you can find everything there. If you have any problems, you can ask me next Wednesday on my personal room. You have any lecture during Wednesdays afternoon, 5 to 6? Yes, so some of you yes, some of you no. If you have lectures and you want still to see something with me, please write me and we can see it in a different time. I don't want to bore you too much, but I don't want you to lose anything. Also because the next passages are very quick. So, if you want to leave, you are free to leave. Otherwise, I will go on with the exercise. This is just to finish solving it and to see how to compute the internal actions and reactions in this structure. Okay. Okay, see you guys. So we can just, now that we have found the values of our reactions, of our static unknowns, we have x1, x2, 3, q1, q2, q3, q1. We have the vertical reaction in all these nodes. It is VA, VC, VE, VG, VI. Now, how to compute the vertical equation? Well, that's very easy. We can or apply the superposition principle. So we just solve first the structure without x1, x2, x3. Then we solve only x1. Then we solve only with x2. Then we solve only with x3. We find the vertical reaction at any point, at any vertical support, for each of the load combination, and then we just sum up all the stuff that we found. Otherwise, we can consider all together. Just to be quicker, I will consider all together. But you can check if the results are consistent and they are the same. So a very good way to proceed in this case is to use bending moment. Okay, equilibrium to rotation. So we consider only the beam AC, sorry. We just say trivial. The sum of all the moments with respect to the only of the beam AC, they have to be equal to 0. Otherwise, that beam would rotate. If we just this stuff with respect to this node, the only things that come up into play are VA, which is our unknown, Q1, and then X1. Is it right? Yeah. I hope I don't mess because I solved with the superposition principle. Now I'm trying to do all together. So we have VA times L1, which is the lever arm of VA, minus the influence of Q1, minus because the rotation is this node. If I take positive this vertical one, the rotation of Q1 is opposed to that one, because it's counterclockwise. So minus Q1. So the force is Q1 times L1, because it is a distributed load. The force is the product of the load times the area, the length where it is applied, times the lever arm. And the lever arm is 1/2 of L1, because we can consider all this distributed load as its resultant applied in the midspan. So the lever arm will be, this is the force and this is the midspan. And then minus X1 equal to 0. So VA is equal to, we bring this stuff on the other side, we have, this is a Q1 times L1 to the power of 2 over 2 plus X2, everything over L1. So this is VA. X2, you're perfectly right. Thank you. This was X1. That's how I make mistakes. Then, in the same way, we can find the VI. It is just the moment with respect to the node G of the beam GI. Equal to 0. I don't write all this stuff because it's very easy. VI is equal to Q1 L1 over 2 plus X3, what is it? I did not write it, okay. But it will be X3 over L1. Why did you want to do? Okay, do. Then the rotation of all this stuff of beam AB, AC and CE or AE with respect to node E. It means that we have VA and we know what VA is. We have Q1, we have Q2, we have X1, and we know the value of X1. We only have VC, we don't know. And then we have X2. So it is depending to the moment, the equilibrium to rotation with respect to the node E of the beam of the beams AE equal to 0. And our aim is to find VC. VC, we write all this stuff. I don't go into details because that's quite long. It is Q1 times L1, because it is the force applied in this beam, times L1 the lever arm, which is, if Q1 times L1 is applied here, its lever arm with respect to the node to the pole E is L2 plus 1/2 of L1. Ah, that's right, okay. Plus the term associated to Q2. Q2 times L2 times L2 over 2, which is the lever arm of that force. This is, okay, let's say that this is times L2, otherwise it gets messy. So, VC has the lever arm L2. It is better to split all the terms. Minus VA times L1 plus L2, because the lever arm of VA is L1 plus L2. And VA is coherent with VC when we bring VA on the right-hand side of the equation, it changes sign and we get minus. Then we have the effect of x2. Okay, we have no effect of x1 because we have both x1 associated with, applied with this counterclockwise reference and with the opposite direction. So it does not come into play. We only have x2. VC, okay? Not this one. Plus x2 times L2, plus x2. Then we can just divide everything times L2. And this is the value of VC. Then, okay, we have that VG obviously is equal to VC because the structure is symmetric, and I will not show that. Then we have VE, which is the best way to find VE is just make the sum of all the vertical forces. So we have that VA plus VC plus VE plus VG plus VI minus Q1 times L1, Q1 times L1, Q2. All these terms have to be equal to 0. All the y terms have to be equal to 0. And we find that VE, I'm not writing the original equation, but the solution is, if I have it. Okay, yes. Okay, that was trivial. It is Q1 times L1 twice, plus twice Q2 L2 minus VA minus VC minus VG minus VI. And this is equal to V for symmetry. Okay? if we substitute all these values, and we substitute Q1, L1, Q2, L2, also in these other terms, we will end up with the numerical value. And you can use Excel to compute it quicker, for example. Then, last step, and we will do it only for the first two beams because it is symmetric, the structure. Now we have found all the values of the external reaction. Okay? What we need now is only to find the internal action. So, shear force, axial force, and bending moment. Can I clean this up? Yes? Okay, let's start with this beam. We will do it only for AC and CE because then it is symmetric. This is node A, VA. Q1. We cut this beam as a generic axis X1. Let's say A, C, N, A, C, computed at X, shear force in this beam computed at X. Okay, I forgot about that. Here we had also the HA. HA, which obviously is equal to 0 because there is no horizontal force applied to the structure. Please notice that this is a typical configuration for bridges, where we have usually, maybe, often, one fixed point where you have no displacement. All the internal supports and the abutments at the other end allow some motion because they have to account for the thermal expansion and contraction during summer or winter of the structure, so that they allow some kind of motion. This is true for bridges. This is not true for beams and columns in common structures because that displacement will not be so big. Okay, we can go on. We have, obviously, we compute the horizontal equilibrium of this part of the first beam, and we find, let's write everything, X equal to 0, means that we have, what a surprise, no axial force. Okay, so this is equal to 0 everywhere. Then, vertical equilibrium equation, we find the value of the shear force. T X AC, we would have this positive for reference, minus VA, plus Q1 times L, because the first depends on the length. But we take all the stuff on the other part of the X of the equation. So the signs vary, and we have VA minus Q1 times X. Now, the shear force is not constant, but depends on X. So, in the axis equal to 0, we have that this is multiplied times 0, disappears. It is, the shear force is equal to the reaction. That's what we expected at the very beginning of the structure. Whereas it linearly increases along the length of the span until it reaches its minimum in the node C, where we have the A minus Q1 times L1. These are the two extreme values. Now, the bending moment. The bending moment is computed finding the moment of all the forces with respect to this node. We have no contribution of shear force or axial force. We only have VA and Q1. So MAC on the generic system X is equal to VA times X minus Q1 times X over 2. Because Q1 times X is the force, it is applied at the mid span of the generic X. So again, it is not linear, it is quadratic, because here we have X to the power of 2. But the bending moment varies from the minimum value, that is 0, because we have one change in the node A, and this term is 0, this term is 0. This other term is VA times L1 minus Q1 times L1 to the power of 2 over 2. Do you know how much is it? Any guess? Will it be equal to something that we have already seen, if you want to check the results? This is the bending moment of the node of the beam AC in the node C. Does it remind you of anything that we have seen during this exercise? Also people at home, if there is still someone. Yeah, a lot of people. No, not a lot, I don't know. And I guess this is the only intelligent thing that you have to think about now. Any smart idea? I mean, you're doing just computation head down, you're writing a lot quick because you know you keep on making some mistakes. I do them. And you get bored of all the mistakes you do. You want to end up quickly. You end up with this stuff. You substitute the value of VA, L1, Q1, and L1. You end up with a number that is -5, I don't know. And you want to know if -5 is right or wrong. What do you have to compute this with? Oh, I know that you know. Okay, great. Why are you shy? Yeah, the bending moment in this node has to be equal to x1 that we had computed before. Okay? Then we can go on. We just see the last part, that is the second beam. I mean, the equations are always the same. You have Q2. In the node C, you will have BC. You also have N, A, P applied in the node C, which was equal to 0, so why am I drawing it? Pointless. You have this force that was equal to 0. You have this force on the other direction. That is T, A, C, computed in L1, because it is the shear force that this beam is exchanging with this one in this node. The bending moment, we change the direction of the bending moment for the principle of action and reaction. But the value is the moment of AC computed in the node C or in x equal to L1. Then we would have x1 in this direction and x1 in the other direction, so they cancel out each other. We consider a generic x starting from the node C. We cut here. We have n C E at the generic axis x, the shear force, and the bending moment. The equations are always the same as before. We end up with NCE compute in x is equal to 0. So we have that this is always equal to 0. Then we have the shear force in the generic axis x, that is equal to the shear force that is transmitted by the previous beam, so TAC computed in L1 plus VC minus Q2 times X. Again, it depends on X. So we can compute the value in 0, and it is equal to this stuff. Okay, because this term goes to 0 because we are in the node C, and then in the x equal to L2 of this is because I'm running. The shear force in the node in the beam CE is equal to same as before, L1 plus VC minus Q2 L2. Okay, you substitute all the values, you get the true result. It will be minus 27. I don't know what something. And finally, the bending moment CE. We still compute the bending moment, the moment of rotation, all the forces with respect to this pole. Okay, that's trivial. No, okay, I will write it just to be complete. The moment of AC in L1 plus we have the shear force of the previous beam and the VC, which has same lever arm. So it is T L1 AC plus VC, which has lever arm X. And then we have the external force minus Q2 times X to the power of 2 over 2. Okay. Again, as before, we can compute the value of the in x equal to 0 and in x equal to L2. Only one thing that is important to remark: the shear force in the node CE at the beginning, so in the node C, is equal to the shear force in the node, in the same node, but belonging to the previous beam. So we are just saying that Okay, we consider this node. We consider what happens to the shear force right before and right after this node. They are equal, but there is a discontinuity of VC. So when we have a force applied, the shear force just has a discontinuity equal to the force applied in that node. So that's done. If we want to draw the diagrams, I'm not drawing the diagrams because that's too long, but I will just, I will not substitute the values, but if we want to draw the diagram of the axial force, always set the reference. So the tensile force are positive, but the shear force, the axial force is always equal to 0. So the first diagram is trivial. Here we have node 1, node A, C, E, D, I. For the shear force, again, we decide some reference, and this has to be the same reference we used for computing the stuff I computed before, and I have cleaned it up because I am very smart. But the same reference is if we consider this side of the element, the shear force is positive going downwards. So the result will be a diagram like this. Where this value is equal to VA, this value is equal to VA minus Q1 times L1. Then we have VA minus Q1 times L1 plus VC, that is this shear force, what I told you before. If we look what happens on this left-hand side and on the right-hand side in the node C, we have a discontinuity. Okay? And we can check these results with Telaio2D that you have seen. It took me like 1 minute to draw the entire stuff. And then finally, the bending moment. The reference for bending moment is the same as before. Basically, we draw the bending moment on the side where we have positive tension, where we have tension. So in the beginning, in the node A, C, E, D, I, here we start with value equal to the bending moment in this node is, can you guess? 3. Is 2. Is, 0. Okay, cool, because we have an hinge. Okay, and that's what we found here. The bending moment in the first node is 0. Then is this stuff, which was equal to x1. Okay. Then we find something x2. Then we find something x1, and then again to 0. That's all. Okay. If you want to compute the maximum bending moment here, you have to say, okay, I don't want to compute the bending moment in this beam. This is L1. In 0 or in L1, but for example in L1 over 0, over 2. To be sure to find the maximum bending moment, we have to find the axis where the shear force is equal to 0. So, for example, this is just the last thing. If we want to know where the maximum bending moment in the first beam is, we just write the equation of the shear force. We say that the shear force at the generic x signed AC has to be equal to 0. Because the shear force is the derivative of the bending moment. You have seen it with the elastic line. So the maximum and the minimum bending moment are where the shear force are equal to 0. So I want to know where this shear force is equal to 0. Obviously, we have VA minus Q1 times X signed equal to 0. That's trivial. We have X1, X signed, sorry, equal to VA over Q1. We compute this ratio, we find 7 meters, and we know that this distance is X signed, and where we have 0 shear force, we will find the maximum bending moment. And so we can compute M in X signed, the beam X AC. And it is VA times X signed minus Q1 times, what is it? It's to the power of 2 over 2. This is the maximum bending moment we can find in this span. Okay. So thank you for staying with me so far. But now I have to end up the record.